Hello everyone, welcome to discussion week 4. Today we are going to be going over cryptography again with a focus on asymmetric cryptography and as well as preserving integrity when we send each other encrypted messages. To begin, I'm going to be going over some concepts that we will need to know for today's discussion. If you feel like you have a good grasp of everything up until this week, go ahead and skip my little mini lecture and go straight to the problems. But to introduce this week's discussion, we are going to be going over 2 different types of asymmetric encryption. The first one is going to be called Diffie-Hellman. And Diffie-Hellman exchange basically means, let's say Alice and Bob want to talk to each other. So we have Alice and Bob. Right? Alice and Bob, prior to sending each other messages, they are going to agree on a prime p, a large prime, as well as some number g, where g is between 1 and p minus 1. All right, and so these 2 values are going to be public. So these values are going to be seen by anybody, any eavesdroppers, so on and so forth. And now what Alice is going to do is Alice is going to pick some secret value A. And Bob, as well, is going to come up with some secret value B. And if Alice is here and Bob is here, Alice is going to send Bob the value of G to the A mod P, and Bob is going to send Alice G to the B mod P. And then what they're each going to do is they're going to both calculate some shared key. So they're both going to calculate a shared key. What Alice is going to do is she's going to take the value that Bob gave her, GB mod P, and she's going to take this value and raise it to her secret value A. And that's going to give her G to the A B mod P. Bob is going to do the same thing, but the other way around, where he has GB mod P. He has GA mod P, and he's going to raise this value to the B. And he's going to get the same exact thing, GAB mod P. And this is going to be their shared key. Right? So you can imagine we have like some eavesdropper E, right? So Eve is going to see both GA mod P and GB mod P, but the problem is she does not have the secret values. So Eve does not have the secret values A or B. And so she can't actually determine, given GA mod P and GB mod P, she can't actually determine what A and B are. So she is unable to actually compute the value of G to the AB mod P. There's no way that she can feasibly compute the value of G to the AB mod P. And so once Alice and Bob have this shared key here, key equals G to the AB mod P, they can now essentially begin symmetric encryption, symmetric cryptography scheme, right, using some shared symmetric key K. All right. Yeah, so the second scheme we're going to look at is very similar to Diffie-Hellman, and it's called El-Gamal. El-Gamal encryption. And so what about El-Gamal, how that goes, it's very similar. We have a prime P and a value G, where G is within 1B P minus 1. And what we're going to do here is, let's say Bob and Alice are once again trying to send each other messages. Bob is going to come up with a value B. And then he's going to come up with, this is going to be his private key. And then he's going to come up with some public key, where the public key is equal to G to the B mod P. Looks really similar to Diffie-Hellman, right? So let's say Alice now, Alice wants to send something to Bob. What she's gonna do is she's gonna, one, pick some random value R, and then calculate her ciphertext to be GR mod P, and then her message M, so this is her message, M times Bob's public key B to the R mod P. And this value we can call big R. So anytime you see like G to the R, G to the B, so on and so forth, you can imagine that as defined as some big R, or in this case, like big B, and so on and so forth. So a little confusing, right? But we can see that Bob can actually decrypt Alice's message using his own private key. So Bob will decrypt by doing this. Bob is going to decrypt by calculating R to the negative B times S mod P. So this value is going to be S, their secret message. And what this is going to give him is essentially R here is what Alice had stored as her ciphertext, right? G to the R mod P. And then the negative B, Bob can easily do by raising this value to negative B because he has his own private key B, right? So this is just raising R to his own, the inverse of his private key, which he can determine really quickly. And then he's going to multiply that by S, which is equal to M times B to the R mod P, right? Which is also equal to G to the R mod P. We can just assume that's considered at the very end, right? So we have G to the R to negative B times M times, what is big B? Big B is G to the B R, right? Mod P. So this value came from here. So now that we have that, we can easily cancel out G to the BR with this value here, G to the negative BR, right? And then in total, we get M mod P back, which is Alice's original message. Cool. A couple of other things. We are now going to consider integrity, right? So with cryptography, like the encryption schemes that we've talked about how these encryption schemes provide confidentiality, right? If Eve is trying to eavesdrop between Alice and Bob, she actually can't figure out any of the messages based off of these encryption schemes. However, one thing we have not figured out is if Eve wanted to corrupt the message that Alice sends Bob, Bob wouldn't actually have a way of knowing that Eve has corrupted the message, right? And so now we're going to talk about MAX, which is just message authentication codes. And so essentially, MAX you can think about as some kind of formula, right? Where Alice wants to send a message to Bob. But she's going to calculate the message authentication code. So we can think about it as like MAC of M and some key K that Alice and Bob both have. And then this is going to give some tag T. And so Alice is going to send both the encryption of M as well as the tag of message M. And Bob is going to be able to verify the tag by doing some type of verification, right? So Bob can decrypt the message M and then do verify of tag and M to determine if the message M has been corrupted or not. And so there's a couple of MAC authentication formulas out there, but one of the best ways that we can do this is using hash functions. And the way that hash functions work is just we have some input of varying size, right? And then what the hash function outputs is an output of a set size. So you can imagine this output always being 128 bits or 256 or something like that. But it's always the same regardless of how big the input is. And so you can think about it as like some type of fingerprint. And hash functions are great because given the fingerprint, you actually won't be able to like take the inverse, right? You wouldn't be able to go back from the fingerprint to the original function, or not the original function, the original input. And so that's what we call a one-way function. And there are other couple of properties. I don't want to go into detail too much, but essentially you can think about it as given an input, we can come up with some fixed size output that acts as the fingerprint of the input, but there is no way to predict what this output is going to be. And so we also think of hash functions as being pseudo-random. So oftentimes, we can take a hash function and turn that into an HMAC, in which case we have a hash function which takes in a message M and a key K that Alice and Bob share. And you can imagine, as before, Alice can hash the message that she wants to send with some key K to get the tag, and Bob can later on decrypt the message and then verify that the tag is correct given the message that Alice has sent. And so a couple of things is MACs are not guaranteed to prevent leakage of information from the message, but HMACs are. So if you use HMAC to come up with a hash of a message M, you can guarantee that there will be no information leakage about that message, but you cannot not necessarily say the same thing for MACs. So with that, we can get started on the discussion. So here we have the first question here, which is about Diffie-Hellman key exchange, right? As you can recall, there are values A, B, G, and P. So which of these values are publicly known and which one must be kept private? So as we said earlier, the public values are going to be our prime P and our value G. And A and B are going to be kept private. The next part says Mallory can eavesdrop, intercept, and modify everything sent between Alice and Bob. Alice and Bob can perform Diffie-Hellman to agree on a shared symmetric key K. After the exchange, Bob gets the feeling something went wrong and calls Alice. He compares his value of K to Alice's and realizes that they are different. Explain what Mallory has done. So like we said before, Alice and Bob agree on a key K by sending each other their G to the A mod P to Bob, or Bob sends Alice G to the B mod P, right? And then we get K from raising one of the values that they sent by the other. So G to the B mod P raised to the A is G to the A B mod P, right? Like how could Alice and Bob end up with different values for their key? What has happened is, let's say Alice and Bob are here, right? But then Mallory is in the middle, right? And so what happens is Alice has tried to send Bob her public key G to the A mod P, right? And Bob has tried to do the same thing to Alice, where he has tried to send G to the B mod P. But what has happened is Mallory has intercepted in the middle, right? And what she can do is she can send Bob and Alice her own key. She can send Bob G to the M mod P, G to the M mod P, right? And what happens is Alice is going to try to come up with the key, and she's going to get G to the M A mod P. And Bob is going to get G to the M B mod P. Right? So Bob and Alice are wrongly assuming that they're communicating with each other when in reality, Mallory has performed what is called a man-in-the-middle attack, where she has intercepted both messages and sent them her own key pretending to be Alice and Bob. So next up, Alice and Bob want to prevent Mallory from tampering with their keys by attaching a hash to each message. So Alice sends the hash of H of her key G to the A, and Bob sends the same thing, hash of G to the B. Does this successfully stop Mallory? So this actually would not be able to stop Mallory, assuming we have the case from above, right? Mallory could not only send her key G to the M, but she can also easily compute the hash of G to the M as well, right? Hash functions are definitely public and anybody can get the hands on them, right? In this case, the hash doesn't take in some key K that Mallory doesn't know. And so there's nothing stopping her from also computing the hash of her own key. So this doesn't actually provide any type of authentication. And so this would not stop Mallory. All right, what about the next case, where Alice and Bob decide to not take the hash, but take the MAC? Ooh. They take the MAC of their G to the secret value, but now you see that they have a shared symmetric key K, right? And they use that key K to determine the MAC of their key. In this case, Mallory actually cannot interfere between Alice and Bob because Mallory does not have that symmetric key K, which means that even if Mallory came up with her own key G to the M or something like that, Mallory would not be able to compute MAC of K of G to the M because she does not have K. You can think of this as like similar to like the block ciphers, right? Where if you don't have the key K, you can't actually compute the block cipher mapping. This is the same thing. Mallory is unable to compute the MAC without the key. Yeah, so this would successfully stop Mallory. All right. The next question is about perfect forward secrecy. So in this case, Alice and Bob want to communicate using some shared symmetric key encryption scheme. We have two key exchange protocols that we went over earlier. We have Al-Gamal-based key exchange and Diffie-Hellman key exchange. And the descriptions below just kind of explain a little bit again about how the two work. So we have some additional details. For one, we can consider PK of B to be Bob's long-lived public key. And then we have K, the Diffie-Hellman components A and B, and the messages themselves are destroyed once all messages are sent. That is, the values are not stored on Alice and Bob's devices after they are done communicating. So in our question, we have some eavesdropper Eve who records all communications between Alice and Bob, but is unable to decrypt them. At some point in the future, Eve is lucky and manages to compromise Bob's computer. So is the confidentiality of Alice and Bob's prior Al-Gamal-based communication in jeopardy? So if Eve is able to compromise Bob's computer, we see that the additional details here say nothing about Bob wiping his secret key B for the Al-Gamal exchange. And so in this case, Eve would be able to compromise Alice and Bob's communication because she has access to Bob's secret key B. As we said earlier, when Alice sends Bob a message, she sends it equal to G to the R mod P for her value R. And then she sends her message times B to the R mod P. Right? And so Eve can easily calculate the message by doing what Bob would have done, right? She could calculate G to the negative B R mod P because she has access to the secret key, and then can multiply that to the message M times B to the R mod P, which is just equal to G to the negative BR times M times G to the BR mod P. which just equals the message M. So yes, Eve would be able to decrypt everything. What about Diffie-Hellman? So if Eve got a hold of Bob's computer this time, she wouldn't be able to get any of the Diffie-Hellman exponents, right? She wouldn't be able to get B from Bob. And so she wouldn't actually be able to decrypt Alice and Bob's Diffie-Hellman based communication, right? She would see Alice's message once again as G to the A mod P, and then she would see Bob's message of G to the B mod P. But because she doesn't actually get access to the secret value B, she is not able to get the secret key G to the AB mod P. And so in this case, she would not be able to decrypt any of their messages. All right, so let's move on to the last problem. So here we have Alice and Bob once again, and they want to communicate with confidentiality and integrity. And in this case, they have some symmetric encryption. They have a hash function, like we said earlier. They have a MAC scheme, and then finally they have a digital signature scheme. So I didn't go over this earlier, but a signature essentially is like the asymmetric encryption version of a MAC, where we have, let's say Alice, she has a public key A and a private key lowercase a, and what she can do is when she, say, sends a message to Bob, she can sign her message. So Bob also has big B, lowercase b. She's going to use Bob's public key to encrypt her message M. So you can think of like encrypt with Bob's key B and M. And then she can also sign her message. So all she has to do is hash M. And then you can imagine some signature scheme where she signs it with her secret key A. And then Bob can verify that this message was sent from Alice, basically by using Alice's public key. And then you can imagine like some verify scheme with H of A and then her public key, which would help figure whether or not this message has been interfered with and whether it came from Alice. So given these cryptographic tools do not interfere with each other when used in combination, we can safely use the same key for encryption in MAC, even though normally you're not supposed to do this. So given these 6 options, which ones can Bob decrypt? Let's go over them. So the first one is a hash of the encryption of K and M. So this one, Bob would not be able to decrypt, right? Because hash functions are only one way and they are also collisions. So given the hash of a message, there would be no way of going from the hash back to the original message itself. So not 1. What about 2? We have C1 equal to the encryption of K and M, and C2 equal to the hash of the encryption of K and M. So in this case, Bob has access to the key K, right? And so he can easily decrypt anything that is encrypted using the key K. And so Bob would be able to decrypt 2. We see, again, using the same encryption scheme, Bob can decrypt number 3 as well. And again with 4, because 4 uses the same encryption scheme. Again with 5, we can't decrypt like a digital signature. It's very similar to a hash, where Bob actually can't decrypt the digital signature of that Alice has sent. But Bob can decrypt number 6 because number 6 is also, once again, just the same encryption as 2, 3, and 4. All right. Next up, consider an eavesdropper Eve who can see the communication between Alice and Bob. So which schemes of those decryptable in part A also provide confidentiality against Eve? All right, so let's look at 2, yeah? So we have the encryption of K and M, and because Eve does not have the secret key, she cannot decrypt that. And we also have a hash of the encryption of K and M, which Eve also cannot decrypt. Bob can't even decrypt that, even if he has the secret key K. And so 2 is fine. What about 3? we have the encryption here that Eve would not be able to decrypt. But then we see here we have the encryption, or we have the MAC of a secret key K and M. And as I have said earlier in the little mini lecture, MACs don't actually guarantee no information leakage, right? So in this case, MAC does not necessarily provide confidentiality, which means that Eve can actually potentially find some sort of partial information based off of looking at the MAC, especially because the MAC is not the MAC of the encrypted ciphertext C1, but it is the encrypted version of M. And so if we had MAC of K C1, this would be a lot safer because C1 is already encrypted, right? And so this would provide more confidentiality than in this case where the message is actually exposed. So 3 is going to be is not going to provide confidentiality. What about number 4? So 4, once again, we have the same encryption scheme, and then we have the MAC of K and the encryption of K and M, right? And so 4 is fine because once again, like we said earlier, 4 is using the encryption of K and M to calculate the MAC. And so this does not provide any information leakage because the message has already been encrypted. So 4 is fine. And lastly, we have 6. Over here, we see same encryption scheme, and then C2 is equal to the encryption of K and the signature of M. And so if we're encrypting anything with our secret key K, this is not going to provide any leakage, right? Because Eve does not have access to the secret key K once again, and so 6 is also going to provide confidentiality. All right, now consider a man in the middle, Mallory, who can eavesdrop and modify the communication between Alice and Bob. Which schemes of those decryptable in Part A provide integrity against Mallory? For example, can Bob detect any tampering with the message? So let's look at the ones that we selected for Part A. We have up for contention 2, 3, 4, and 6. All right, so let's look at number 2. So we have our hash here of the encryption of K and M. And so this is actually not going to provide integrity for Alice and Bob. And the way that Mallory can potentially sidestep this is she can replace C1 with her own message M, right? And then for her hash, she can just compute C2 equal to the hash of M. And that's going to be consistent, right? We see the encryption of K and M being directly placed here. And again, our hash functions are public, and so Mallory can easily just figure out the hash of her message by using the public hash function. And so number 2 is not going to provide any integrity. What about number 3? The way that we try to get integrity here is using a MAC of K and M. And so this is going to provide integrity because, like we said, Mallory does not have access to the secret key K, right? So Mallory has no way, even if she tries to tamper with the message, she cannot actually figure out the MAC of a key K and her own message M prime because she does not know the value K. All right, what about number 4? The way that we try to get integrity for number 4 is by doing the MAC of a key K and the encryption. And this is going to be the same thing as 3, where because Mallory does not have the secret key K, she will not be able to forge a correct MAC for her message. So these 3 and 4 are fine. Finally, number 6, we have C2 equal to the encryption of K and some sign SK of M. And this actually does provide integrity because Mallory, once again, not only can she not sign her message M, but she also cannot figure out the key K, right? So this one's also going to be fine. So the answer for this one is 3, 4, and 6. To go in depth about the signing, Mallory cannot sign because she does not have the secret key that only, say, Alice has, or the secret key that only Bob has, right? There's no way for Mallory to sign with her secret key that Bob and Alice could decrypt with the other person's public key. So 3, 4, and 6 are good. All right, lastly, many of the schemes above are insecure against a replay attack. And what a replay attack just means is, let's say Alice and Bob are sending each other messages, right? And Mallory intercepts these messages. What she can do at a later time is take this message that, say, Bob has sent Alice and send it to Alice again. And Alice will just assume that Bob has sent her the same message again, not knowing that Mallory has done a replay attack by sending the message herself. And so how can we modify some of these schemes with confidentiality and integrity to prevent replay attacks? So the two schemes that we have that both provide confidentiality and integrity are schemes 4 and 6. To quickly review, 4 has the encryption of K and M, and then the MAC of K and the encryption of K and M here, and then 6 has the encryption of K and M, and then C2 is the encryption of K with the signature of M using the secret key. And so the way that we can prevent against replay attacks is basically by tacking on some unique timestamp to the end of the messages. Instead of M, we could do M concatenated with some timestamp. M concatenated with like 1, M concatenated with 2, M concatenated with 3, and so on and so forth, where this number is never repeated, right? And then in that case, what's going to happen is, let's say like Mallory intercepts this message too, right? And then she'll try to send it to, say, Bob again. But Bob is going to like decrypt the message and see that the timestamp tacked to it is 2. And we've already seen that number before. And so he knows that this is going to be a replay attack. And so a way that we could modify both schemes is to tack on a timestamp to our message M. So essentially replace M with M and some time T. Yeah. So this is the end of our discussion. Thanks for hearing me out all the way through. Hope you all have a good week, and I'll see you all next